So quick poll before we start. How many of you have heard the term LDFI before? A few. How many of you practice some form of chaos engineering at work? Great, that's a lot of hands. How many of you have read this paper before? Some, okay. So we are, I'm Ashutosh and this is Ram. We are site reliability engineers at eBay, and today we want to talk about Madaari, the next evolution of LDFI, which we have sort of done at eBay. Okay, so what do we want to talk about today? We want to talk about distributed systems, the problems that come with such systems. We want to look briefly at chaos engineering, what we have achieved so far in the industry, of all the techniques that are available. Then we want to look at lineage driven fault injection, how it was and how we have evolved it over the last year. We in particular want to talk about why ordering of faults matters for all chaos engineering experiments. And then we want to talk about in some detail about how you can bring LDFI to your enterprise as well. And then hopefully towards the end we'll share some results that are interesting to everyone. Okay, so before we begin, this is joint work between eBay and University of California, Santa Cruz. The lab is headed by Dr. Peter Alvaro. So yes, once in a while when he's not at the beach or breaking his foot or breaking his nose, we do get some work done. And in case you are wondering about the title is derived from a Hindi word Madaari, which means a person who orchestrates the monkey. So hopefully by the end we have learned how to tame the monkey and make it do more useful and wise things. Okay, so over the last few years, microservices architectures have become kind of the rage. They come with their own set of problems. And the complexity is not only in the infrastructure, but also in the telemetry and monitoring solutions. These applications are often cobbled together using software components that are thought to be fault tolerant. But you and I know that fault tolerance is an end-to-end property and it does not compose. As developers, we want to make these individual software components fault tolerant. As SREs, we want to test the end-to-end fault tolerance properties of the system with minimal effort. So why is this hard? So consider an application running with, let's say, 100 microservices. 100 is not a large number anymore. So if you are looking for one fault cardinality, you are only looking at 100 faults or 100 sort of failure modes. As soon as the fault cardinality increases to 4, you may have to run up to 3 million experiments in order to find out, oh, well, the system is okay or not. So what has the industry done about it? The industry in the past, we used to do unit testing, integration testing, model checking, but we know specifying these specifications is hard. And even when we do, we are not able to actually test the parts of the code that provide the resilience or the recovery of the application. And from intuition and experience over the last few years, we know failure is inevitable in production. So we might as well inject it in a controlled environment. And that is exactly what chaos engineering does. It's this technique of proactively perturbing and then observing the system to understand whether it will tolerate that particular failure or not. And the failure can be network partition, node reboot, certificate expiry, GC pauses. All of these are legitimate modes of failure. Now, before we go any further, let's look at two of the popular ways of doing chaos engineering in the industry. The first one has no model of the system. We essentially treat the system like a black box, and then we roll the dice, inject a fault and see what happens. Chaos Monkey is a popular implementation of this technique. It's extremely successful, as is evidenced by its popularity. In the other world, you can have a genius like Ram who holds the mental model of the system in his head. This mental model is, he had arrived at this mental model by observing successful executions of requests in production. This model is further augmented by talking to the people who develop the actual product. Now, with that mental model, the genius can guide the fault injection infrastructure to do fewer things and probably in a smarter way. Both of these techniques, while important and necessary, are inherently not scalable. Why do I say that? With the first one, you cannot quantify what progress you have made. We do not know how far we have gone into the space of fault exploration. Have we explored all of the faults? Have we explored at least the critical ones? Am I ready to ship? And with the second technique, we know that there are only so many SREs you can have in your organization, and human beings in the loop are inherently limited. Okay, so with this intuition, let's move on to talking a little bit about LDFI, or Lineage Driven Fault Injection, which alleviates some, if not all, of the limitations of the techniques that we have seen. Before we go into LDFI, I'm going to make a claim that fault tolerance equals redundancy. Why do I make that claim? I'm able to make that claim because every execution that succeeded in production, in spite of a fault being there, succeeded because the execution was able to take an alternate path in the system. Therefore, at every single request that was fault tolerant had to have taken a redundant path in the presence of faults. Now, as SREs, the most difficult question we ask ourselves is, why did things go wrong? Now, as with most things in life, the easiest way to answer that question is to change the question altogether. So let's ask ourselves a different question. Let's ask why things went right. LDFI is going to use this question and the answer to this question to model the system's redundancy. It's going to observe successful executions and then understand why those executions were successful. Okay, so let's peel the cover of LDFI one bit at a time. What do we need? We need a recipe to make all of this work. So let's start with a successful outcome. And for example, an HTTP request that gave you back a 200. Let's work backwards from there and try and understand why that request succeeded. The answer to that question lies in the lineage of the request, the path that it took within the system. We'll get to the lineage part in a little bit. Once you have that lineage, we can model that lineage or system's redundancy in conjunctive normal form. I'll get to that CNF formulation also in a little bit. Once you have that CNF formulation, you can feed it to a SAT solver, and the solutions that come out of the SAT solver are basically the next set of faults or failures to be injected. Now, when you inject a failure, there are two things that can happen. Let's say the next request fails, in which case you have successfully found a bug. So let's go ahead and fix it, and then we can come back to running the experiments again. In the other scenario, the request may succeed, in which case LDFI has discovered the redundant path within the system, the way the system provides redundancy in light of a failure. Okay, so now let's move on to developing some more intuition around this encoding bit that LDFI does. How do we do that? Let's take the simplest possible execution, a 5-node call graph. What would it take for this execution to fail? This execution can fail if A fails, or B fails, or C, or D, or E. Okay, let's say we decide to fail B, and the red node B looks like possibly a failed RPC call. Now, how can the second execution rather possibly fail? It can fail if A fails, or C fails, or D, or E. Now, LDFI will do quite simply an AND over these ORs to model the system's redundancy. We understand from this formula that in spite of a failure being present in B, the system was able to succeed. The next thing that LDFI will do is take this exact formula and then attach more, and as we do more experiments and get more call graphs, the formula becomes bigger and bigger, and eventually feed it into a SAT solver and then arrive at a solution for the next set of faults. Okay, but there are some limitations to this approach. As I showed earlier, the space of faults that can potentially be explored is quite large. LDFI, even after using SAT, while it can reduce the search space, the executions where the number of nodes is quite high, the search space can still be very large. Secondly, SAT being a decision problem, it gives no ordering for the faults to be injected. Now, why does that matter? Why do we care about lack of ordering? Our intuition as SREs is that some services are more likely to fail in production than others. We know that. How do we know that? We know that because of the incident histories attached to a service and through some other mechanisms as well. So what do we want to do? We want to find the most likely faults first, and we want to reduce the search space for the experiments. We want to conduct as few experiments as possible to get the biggest bang for our buck. Also, we want to do overall more experiments per unit time. Okay, so let's develop some more intuition around how can we possibly achieve this. First, let's consider a simple, again, a call graph. Let's say you decide to inject a fault or some failure in F. The failure of F is going to manifest in E. The failure of E is going to manifest in C. Similarly, the failure of D is also going to manifest in C. Now, what if I decide to fail C and the execution succeeds nonetheless? Then I can prune away the entire subgraph below C, and I no longer need to inject any faults or do any chaos experiments there. Okay? So once I'm able to do that, I can arrive at a much simpler call graph. And the point being that when we needed to make a choice between all of the faults B, C, D, and F that we could inject, strategically injecting a fault in C helps me prune away a large portion of the fault space. So what did we do and how did we do this? We used the structure of the graph at hand to be able to make a judgment. The rank of the node, which is basically the distance from the root to the node, the size of the subgraph if you want to break ties below the node, and as I mentioned earlier, if you survive the failure of C, you will surely survive the failure of D, E, and F as well. Okay. So let's strengthen this intuition further because we are all running in production. We know all services are not created equal, and we know that with this containment hierarchy, that node failures are more likely than rack failures, which are significantly more likely than data center failures. Also, we know that a service that was released yesterday is more likely to have a bug than a service that was released 3 months ago. That's my intuition, and I want to encode that intuition and feed that into LDFI. We also have these incident histories and bug rates that are attached to services. These are all sort of metrics that I can use to order my chaos experiments and prune away large pieces of the subgraph away, and thereby conducting more experiments per unit time and getting probably better results. Okay. So hopefully by now, through my explanations and visuals, we have developed some intuition for why ordering of faults matters and why we should inject the faults that matter. Next, I'm going to hand over to Ram, who's going to walk us through how we did all of this at eBay and how we use the existing observability tools to be able to achieve all of this.
Thank you, Ashutosh. All right. So let's simplify. Are you able to hear?
Is the mic on?
Hello? Yeah. So let's simplify everything. What do we need to get LDFI up and running? Explanations of why executions are successful, a way to encode models of redundancy, a tool or tool set to do fault injection. With these three building blocks, we can close the loop and run our chaos engineering experiment. Let's look into explanations first. Next, let's put ink to the paper and give concrete solutions on how you can realize these three building blocks in your organization. Let's look into explanations first. What are traces? They are ordered events with context stitched together. Leaving aside the appealing aspect of being able to visualize them as DAGs, we can also map the journey of the request as it makes its way through the system. Distributed tracing provides easiest way of constructing the lineage of a request. While it is not perfect, but usually it is good enough. Well, what if you don't have distributed tracing? Structured logs with timestamp and enough metadata like correlation ID are also good enough. Log stitching is a good technique that can be applied with a reasonable degree of success. We did not have distributed tracing from day one, so we used log stitching to convert our logs to open tracing compatible traces. This is what allowed us to construct the lineage from the logs. In the space of fault injection, there are various options are available, both in open source and vendor closed source world. We had our own set of constraints to deal with, so we decided to roll our own. Of course, when you roll your own, you get to use cute names like Mowgli. Mowgli understands the EBS infrastructure, that is the infrastructure and the application topology of our internal cloud. We have lot of options are available, so we use Mowgli because it keeps track and audit trail and tracks experiments. And if you are new to fault injection, then use simple tools like manipulating IP tables to drop packets is perfectly okay. The most important tip we can share for home-grain fault injections is to be safe by default. Always have a recovery or rollback strategy. Start simple, stay nimble, and don't try to climb Everest on day one. So to finish the closed loop story of an LDFI, we need a way of replaying the same interaction over and over again. One would think this is the easiest bit. As it turns out, this was the hardest part to get it right. The best way to do that is to have an end-to-end test for a system. This can be an API call and assertion on status code, or in case of UI, a Selenium-based test. With APIs, the status codes tend to lie. Well, sometimes anyway. You may have to look up database or something to see if the final state of the transaction is what you expect. For eventually consistent workflows, you have an option of wait and see if the transaction went through while you move to other experiments. You can always come back and register the result of previous execution with the LDFI, and the model would be updated with the new lineage. So let's pull everything together and see how you closed the loop. We start out in a steady state and run an end-to-end test. In our first run, which is our baseline test, the test needs to be successful since at this time we have not injected any fault. Next, we take traces or explanations and convert them into call graphs, and then subsequently encode them for ILP or SAT solvers. The intermediate step of call graph is just for visualizing and useful for debugging. If you are already using distributed tracing, then perhaps you can skip this. Once the solver finishes, it will suggest the fault which needs to be injected using fault injection tool of your choice. For reference, we are also showing some of the libraries we used as part of this entire exercise. So with all theoretical and implementation details figured out, we move on running the experiments. For simplicity, we anonymized the service names and annotated them with the numbers instead. The graph that you see on your screen is the graph of actual microservice interaction as part of our payments platform. The nodes marked in green are services which are known to cause hard failures. We put them in whitelist so that LDFI does not suggest them. We go about exploring the faults LDFI first suggests service 2, we injected the fault, and it turns out we tolerate that fault. This allowed us to prune the subgraph below service 2. Such services are marked in pink. As LDFI keeps suggesting the faults, we end up reaching service 11. We injected the fault, again it turns out we tolerate that fault as well. Since we tolerate that fault, we no longer need to inject the fault in service 23, 22, and 38. This strategic fault injection using ordered faults, which allows us to prune the subgraphs easily. However, if you notice, we did not ignore service 29. Why is it? Because it has a redundant path from the root node 1 to 10, 10 to 21. Service 27 is similar to service 29. We found total 6 bugs highlighted in red. The bugs range from total functionality failures to unexpected outcome and incorrect status code reporting. We discovered both bugs that were known to the product, both new and bugs that were known to the product teams. We concluded this entire exercise in few hours. Overall, we did 17 experiments for a single fault strategy, and we also wrote uniform random fault injector for comparison with Chaos Monkey. It should not come as a surprise that LDFI was more efficient since it prunes away larger fault space very quickly. Using Mowgli is more efficient for our purpose because it does not wait for reboots to finish before we proceed to next experiments. This is what allowed us to conduct more experiments per unit time. Next, we talk about very interesting result where we found no bugs and declared the service as shippable. Once again, we marked the nodes that are known to cause hard failures are in green. We go about exploring the faults. When we hit service 6, it survives its failure. This allowed us to prune the 6 services from the search space. In all, we conducted 7 experiments. So this result is very important because eventually we want to make this as part of our regular CI pipeline. So to achieve that, you should be able to mark the services as shippable in a reasonable amount of time. All right. So far we have seen all the details about LDFI with experimental results. Now I'm going to hand over to Ashutosh to give future direction of LDFI. Thank you.
All right, thank you, Ram. So we were able to see what LDFI using ordered fault injection is able to do. It's able to prune away larger pieces of the subgraph away, thereby allowing us to do more experiments per unit time and getting a bigger bang for our buck. Okay, so what does the future hold for Madaari? As I mentioned earlier, there are lots of sort of metrics that you can combine together, whether it's your incident history, bug rate, time since last release, and structure of the graph itself. We think we can arrive at a single theta, which will allow us to eventually encode the peculiarities of your architecture while LDFI still remains oblivious to sort of what you are running in production. As we are moving to this SLA world where all SLAs are being attached to microservices, we think we can do strategic delay injection to be able to do SLA verification as well. Another really interesting thing that we think we can do and we want to do is reason about stateful systems. So we have a lot of services where state trades hand from one service to another. We think there are rich opportunities to explore bugs and sort of improve the resiliency there. And overall, I just want to re-emphasize that LDFI is a technique and not a tool. So you get to bring your own tools to the party. So whatever be the state of your fault injection or observability mechanism, you get to bring that to the party and sort of plug everything together. Okay, so now time for some opinions, because who doesn't love an opinion? Where do we think chaos engineering as a community needs to go? We think chaos engineering should have 3 Ws as a whole. We want to understand what to inject. SREs are the best people to sort of make that judgment, whether you want to do network partition, node reboot, certificate expiry, whatever catches your fancy. We want to understand where to inject faults, which software component or possibly hardware component as well that we want to target. LDFI can help answer those questions. And now the new thing and the most important thing is we want to have precision for our fault injection experiments. Just to give you some intuition for that, I would like to be able to inject a fault when there are exactly 5 items in the card. As of now, there is nothing available, no technique, no tool available that allows us to do that. But we think we can achieve this. How can we possibly solve this problem? So time is this beast in a distributed system that is very, very hard to track down. Distributed systems have no notion of now. So how can we possibly solve this problem? So let's take a step back and try and understand what time essentially is. Time is that implicit order that you can arrive at or you get through message passing or change of state or events in a distributed system. So if you have an event log where events or change of state is being logged, we think we can arrive at time just by looking at that log. Think event source systems for intuition. And then once we have that, we can make this journey from the domain of time to the domain of state and then back to be able to arrive at precision for our fault injection. Once we make this journey, then all that we need to do is come up with a predicate that a service can evaluate over its local state. And then decide, oh, do I have 5 items in my cart? Yes, if I do, then that's the right time to inject a fault. We think we can solve this problem too. Okay, so what are the key takeaways from the talk today? We learned that industry and academia can work together. We looked at limitations of LDFI as it stood using the SAT solver and why ordering of solutions matters. We understood how LDFI can be integrated into the enterprise by using the existing tool set that you have. We also shared preliminary and hopefully interesting results on how ordered fault injection is much better than uniform random fault injection. And the last bit of tip that we want to leave you with is evangelizing these new techniques within your organization can be hard. So start small, stay simple, and hopefully all of you will have success in bringing chaos engineering and LDFI to your enterprise. Thank you.